So let's talk about the electric force that a charge exerts on another charge. This equation is called Coulombs Law. It is specific for the electric force on a point charge, meaning the charge is concentrated at a small point. So Coulomb's law describes the electric force on a point charge due to another point charge. We'll talk about finding the force in some other situations a little bit later. So Coulomb's law can look a couple of ways. The basic setup looks like this. Oh, excuse me. Now, this over here, the 1 over 4 pi epsilon naught, this is all a constant. Epsilon naught is called the permittivity of free space. You don't really need to remember the name. But the value is 8.85 times 10 to the negative 12. It has units of Coulomb squared over Newton meter squared. So when we take 1 over 4 pi epsilon naught, we're always going to get a constant. We often use a K and sometimes a K sub E to represent that. When we plug that in, we get 8.99 times 10 to the 9th Newton meter squared over Coulomb squared. So we might see this force just written this way rather than writing out 3 constants. Just plug it in as one big constant. Either way is fine. Either way we write it, everything here or here is the magnitude of the force. And specifically the electric force. So the force that a point charge, like a proton, exerts on another proton or on an electron. This equation, this magnitude, if you remember your vectors, or even if you don't, you want to review at this point. Magnitude just means the absolute value, just the numerical portion. How big is the force? So we have a constant. Q1 and Q2 are the 2 charges involved in the force. One of them represents the charge feeling the force, experiencing the force. And then the other charge represents the acting agent. If you happen to remember Physics 1, 2210, we were talking about forces. A force always involves an object that actually experiences the force or feels the force, and then that force is always caused by an acting agent. Now, whether Q1 is the one experiencing the force or Q2 just depends upon the problem that we're trying to solve. So, for example, if we were trying to find the force, electric force specifically, on Q1. Now, I have just chosen to draw both of these charges as positive charges. Since they're both positive, we know they are going to repel because like charges repel each other. So Q1, if I want to draw the vector representing what Q1 would feel, it would experience or feel, I know it doesn't really feel anything, but it just is an easy way to describe it. So Q1 would experience this force pointing to the left because that is the direction that is directly away from Q2. How big this force is, so the magnitude, just the absolute value, is going to be this constant. It's going to be the value of the two charges, Q1 and Q2. And then in the denominator, R represents this distance from center to center. So the amount of charge that both charges have determines the force, but the distance between them is also a factor in determining the force. You might find this equation somewhat similar when we talked about the universal law of gravitation, the force of gravity. It was a constant times the mass of the two objects involved in the gravitational attraction divided by that distance squared. So the form and the look of the equation is similar in that we have a constant, we have characteristics of the object. For gravity, it's the mass, and then this distance squared. Both of these are called inverse square laws because they have r squared in the denominator. What that means is if I have these same two charges up here, but I cut the distance in half, the force, I end up with a 1/2 r, but then squared in the denominator, which means I end up with a 4 times bigger force. If I square the 1/2 in the denominator, I get 1/4, but again, it's in the denominator, which brings the 4 up to the numerator. So a change in distance, we have to square how we are changing that distance to see what effect that has on the force. Now, gravitation, this constant was incredibly small. 6.67 times 10 to the negative 11. Whereas our constant with this electricity, the K, is a very large number. And so electric forces are much more noticeable than gravitational forces, just with that larger constant. All right, in our equation up here for Coulomb's law, you will see this r hat. R hat is a unit vector, meaning it has a length of 1. So if you remember, I hat was a unit vector in the x direction, j hat was a unit vector in the y direction, k hat is a unit vector in the z direction. R hat is a unit vector, but it's in what we call the radial direction. We know that the force that a charge experiences due to another charge is either directly away or directly towards the other charge. So coming back to our picture, we have these two positive charges. Well, since they're both positive, they're both the same type of charge, they're going to repel, which makes the force radially away from the other charge, or just directly away. If you want to think of it this way, let's see, if Q2 was in this central region, I could put my Q1 not only to the left like I have above, but I could put it up at an angle, I could put it directly above, I could put it directly below, some angle over here. As long as the distance between Q1 and Q2 is the same, the magnitude of this force is going to be the same, regardless of where Q1 is located. So as long as the distance this is the same, the magnitude of the force is the same. This one's a little off. Let me draw it better. The only thing that changes by putting Q1 at these different locations is the direction of the force. Well, because Q1 is positive and Q2 is positive, Q1 is going to be repelled. That's upwards for this guy. The one off at the angle is directly along that line R that connects the two. This one's directly away that way, directly down, directly out this way. So if we imagine a circle, we could put Q1 anywhere on this circle with radius R, and it will feel or experience the same magnitude of force. The only difference is the direction. The direction will always point along that radius, and in this case, outwards, because the Q1 is going to be repelled. In any given problem, we will need to write R hat in terms of X or Y. So if we were using our typical Cartesian coordinate system, where X is horizontal and positive to the right, Y is vertical, this force right here would be in the positive J hat direction. This one would be the negative I direction. This would be the negative J direction. But this would have an X component and a negative Y component, meaning we would need to break this force down into X and Y components in order to figure out how much of the force points in the X direction and the Y direction. Similarly, up to the left, this one has a negative X component and a positive Y component. So we will be working with our vector math again, where we're adding vectors together. So we do need to be able to break our vectors into X and Y components and write them appropriately in terms of the X and Y directions. Excuse me. So our equation for force, R hat, you can think of it as a reminder to write the force in vector notation. Oftentimes you will see, and even within our book, you'll see this electric force written with the constant and then the absolute values of the two charges over R squared, R hat. The absolute value is just so that we get right here the magnitude of the force, because remember, magnitude is just the absolute value, the number. It's not a negative, because negative specifically refers to a direction. All right, so let's do a little example here. Let's say I have a Q1 that is positive 4 nanocoulombs. And a Q2 that is positive 6 nanocoulombs over here. And let's say they're 3 centimeters apart. The force on Q1, let me write that as a question. What is the electric force on Q1? So the magnitude is easy enough to, hopefully. So I'm using just this equation, the K Q1 Q2 over R squared. And then I will assume a typical Cartesian coordinate system and put the direction on it. Because force is a vector, I would have to be asked for just the magnitude of the force if it did not want me to account for direction. So I'm going to go ahead and start plugging in. K is this constant, this 8.99 times 10 to the 9. K has units of newtons times meters squared over coulombs squared. Q1 and Q2. For nano, I do need to put the 10 to the negative 9 in because I'm going to need my coulombs to cancel. Q2 is 6 nano coulombs. Let me write my units this time through. Over, for units to work out, since K has meters as part of the units, we do need to put R in terms of meters. So the Coulomb and this Coulomb are going to cancel with the Coulomb squared in the units for K. When we square the meters, that's going to cancel with the meters squared in K and leave us with newtons, which, of course, hopefully, we remember that newtons is the unit for force, the SI unit. So there's K, plugging in my Q's. I'm getting 0.00097. I prefer to use scientific notation rather than write out a bunch of zeros. So this right here would represent simply the magnitude of the force that Q1 is experiencing because of Q2. The question overall, though, because it's just asking us for force, and force is a vector, we will want to get the direction on it. So because both of these charges are positive, we know they are going to repel. So Q2 is going to push Q1 away. That means Q1 is experiencing a force to the left. So in a typical Cartesian coordinate system, this would be the negative I hat direction. And whether we do I hat first or units and then I hat, but the negative I hat represents the direction. The 2.4 times 10 to the negative 4 is the magnitude. So we have accounted for both. Now, oftentimes direction we want as an angle. We could say 2.4 times 10 to the negative 4 newtons at 180 degrees. If you happen to remember, and we talk about direction in terms of an angle, we're going back to the polar coordinate system, where theta is measured counterclockwise from the x-axis. And so to go all the way from the x-axis to pointing to the left is an angle of 180 degrees. So there's two ways we can write our our results. Typically, a problem will ask for a specific way in terms of the angle or in terms of components. And so we will just need to write that answer in whichever way they have asked. Okay, so Coulomb's Law, this equation, allows me to calculate the force on any one charge, and specifically a point charge, due to another point charge. So that means I should be able to use the same equation to find the electric force on Q2 here. So when we talk about Q1 and Q2, one of them is feeling the force, the other one is the acting agent, or the one causing the force. Well, I know that Q2 is going to be repelled by Q1, so its force is going to be to the right. In terms of calculating the force, I need the same constant. I need to know the value of Q1, the value of Q2, how far apart they are. That will be the magnitude. But that's what we just solved for down here. We needed the constant. We needed to know how much charge was on Q1 and on Q2, and then how far apart they are. So I would plug the same numbers in and get the same magnitude, which hopefully makes sense. If you remember Newton's third law, for every action there's an equal and opposite reaction. That means Q1 is exerting a force on Q2 that is equal in magnitude, just size, to the force that Q2 is exerting on Q1. But equal and opposite, this one is in the positive x direction. So Q2 is getting pushed to the right, while Q1 is getting pushed to the left. So equal and opposite forces. Even though they do not have the same charge, they experience the same force. Now, this equation, works well for any setup of charges. So say I have a Q1 that is still positive 4 nanocoulombs, but Q2 is down here. Let's make it negative 6 nanocoulombs. And let's keep them 3 centimeters apart. What will change? So let's scroll a little bit. So we had our 4 nanocoulombs and 6 nanocoulombs. They were along the same horizontal line. This time, I still have 4 nanocoulombs and 6 nanocoulombs, but one is positive and one is negative. What is the force on Q1? Well, because they are both point charges, we would use the same equation. This is where it can be helpful to put in the absolute values, because if we do the absolute values, so we're still doing the 8.99 times 10 to the 9 for K, 4 times 10 to the negative 9, 6 times 10 to the negative 9, not negative 6, over the 0.03 squared, I'm going to get 2.4 times 10 to the negative 4 again. I get the same magnitude of force because the magnitude of those two charges are the same as they were before, and they're still the same distance as I had them before. What's changing is the direction. The direction, here now I have a positive charge and a negative charge, meaning they are attracting. Opposite charges attract. So Q1, I want to draw what it experiences, or if it could feel, what it would feel in terms of the force. Attraction means it's getting pulled towards Q2. And so in our typical Cartesian coordinate system, that would be the negative j hat direction. But if we had been asked for the force on Q2, the magnitude would be the same because it's the same amount of charge on either one. They're still the same distance apart. The difference is that attraction for Q2 is upwards towards Q1. It's getting pulled towards Q1. So this one would be 2.4 times 10 to the negative 4 newtons in the positive j hat. You can write positive if you want. You don't have to. If it's not a negative sign there, the positive is implied. So we're revisiting vectors. Forces acting on an object, and that is a vector which requires us to consider x and y directions. Let's look at one that has x and y components. I'm going to change the values. Let's say I have a Q1. Let's make it negative. So negative 5 nanocoulombs. And a Q2 that's negative 2 nanocoulombs. And let's say this distance is 30 centimeters and this distance is 4 centimeters. What is the force and electric force specifically on Q2 in component form? Meaning in terms of x and y components. We'll find the magnitude and direction as well, just to have the practice. Okay, both of these charges are negative. When we talk about our equation for Coulomb's law, r in the denominator always has to be the straight line distance between the two charges. That straight line connecting the two charges. Now I chose those numbers because I could easily figure out what that was, but I could use the Pythagorean theorem to figure out r, because these met at a right angle. So I could say r was the square root of 4 squared plus 3 squared, which would have given me 5. So 5 centimeters. So the magnitude. Let's go ahead and find the magnitude first, and then we will write this in terms of x and y components. Now, first of all, these are like charges, so we expect Q2 to be pushed directly away from Q1. So that line should be directly along this dotted line connecting the two charges together. So the magnitude, let's do that first. So F magnitude, we have K. I am in the habit of just putting in my absolute values of my charges. So I'm not putting my negative signs on, because I'm going to make sure the direction I'm describing the vector at in the end is correct. So I just want the absolute value, so I put in my positive values for Q. So the magnitude of this force Let me plug that in. I'm getting 3.6 times 10 to the negative fifth newtons. I've changed my calculator to scientific mode to put it in these, what is it called? The scientific notation, 10 to the negative fifth. So that represents the strength of this force. How big of a push that Q2 is experiencing. So this is the magnitude of the force. Now the direction, this vector up here, it has a positive x direction component and a positive y component. It's pointing both to the left and upwards. I'm going to go ahead and just redraw this force down here and draw on these components. The x component and y component always meet at a right angle. We now currently know the length of this hypotenuse, because that represents the magnitude of the force. To get the x and y components, we also need an angle. The angle in here, if I come back to my original picture, because the force lies along the same line as R, this angle in my original picture is the same as the angle that I just drew in my force triangle. So this x component being adjacent to the angle would be the magnitude of the force times the cosine of the angle. Fy would be the magnitude of the force times the sine of the angle. Well, we can find that angle coming back to the original picture. I know the tangent of that angle is the opposite side, which is 3 centimeters, over the adjacent side, which is 4 centimeters. So if I take the inverse tangent of both sides, I get 36.9 degrees. So the x component, I will take the magnitude of the force times the cosine of 36.9 degrees. So my calculator already has these values in it. And I'm making sure my calculator is in degree mode. So this x component of the force, I'm getting 2.9 times 10 to the negative fifth newtons. The y component, I would put in the magnitude again, but now I'm taking the sine, so times the sine of the same angle. I'm getting 2.2 times 10 to the negative fifth newtons. So we could write this force in vector notation. We know this x component points to the right. That's the positive x direction. So I hat. We know the y component points up. So that's the positive y direction. And that's all in newtons. And if we really wanted to, we could factor out the 10 to the negative fifth as well. There's no need to do that, but let me write that better. 10 to the negative fifth newtons. So here is the force that Q2 is experiencing because of Q1 and how they are located relative to each other. If we had asked for the force on Q1 instead, the magnitude would be the same. The only difference would be this direction. Q1 would be pushed away from Q2, so it would have a negative x component and a negative y component. Its force would be negative 2.9 hat, meaning the negative x direction, minus 2.2 j hat, meaning the negative y direction, and both of those times 10 to the negative fifth newtons. So vectors, you might need to brush up on those. One last thing is what happens if we have more than two charges? Coulomb's law is valid only on one charge at a time. So I'm just writing it out again. Let's say we had a Q1, a Q2, and a Q3. Well, depending upon which one we want the force on, for example, what is the force on Q3? And we mean overall, Q3 is going to experience a force because of charge 1, and it's going to experience a force because of charge 2. So charge 1, because it is positive and Q3 is negative, Q3 is attracted to charge 1. So draw the force vector on the charge you're trying to find the force on. Just what is this charge experiencing or feeling because of Q1? We would find F1. We would have our constant. The two charges involved here would be Q1 and Q3. So we just want to include the charges that are involved in that attraction. And then R, it needs to be the distance. I'll call this R1. We just need the straight line distance between those two charges. The direction would be the negative x direction. And so I would put that as part of my vector. Q3 is also being attracted to Q2. I'll call that force 2. So this one represents attracted to Q2. F1 represents it being attracted to Q1. So Q3 is experiencing two forces, which in turn will need to be added together to find out overall the force that Q3 is experiencing. So F2, the magnitude of it is determined by the two charges involved in that particular attraction. The distance we need is this, I'll call it R2, the straight line distance between the two charges. But this vector has both x and y components, which we would need to figure out before we added. So let me go ahead and make up some numbers and we can solve the problem. Let's say Q1 is positive 2 nanocoulombs. Let's make Q2 positive 4 nanocoulombs, Q3 negative 3 nanocoulombs. I'm just making up numbers here. Let's say R1 is 5 centimeters. And let's make this distance between Q1 and Q2, let's make it 4 centimeters. It looks a little bit closer than the top line. Okay, so I'm going to erase F2 for a second so we can go ahead and find F1. So F1 again represents Q3 being attracted to Q1. So it's getting pulled towards Q1, which is to the left. To find the magnitude of the force, I need our constant K, which remember has units of newtons times meters squared over coulombs squared. You don't need to write the units out all the time, but I do once in a while so that I can remind you of what is canceling. So the two charges involved in this attraction are Q1, which is 2 nanocoulombs, and Q3, which is negative 3 nanocoulombs. But again, I'm just putting magnitudes in, and I'm going to account for the direction separately to make sure it makes sense. Because I know Q3 is attracted to Q1, which means it's getting pulled to the left. I need to make sure my vector represents what I'm writing out, what number I'm getting, represents to the left. So I'm just plugging numbers in. Okay, I'm going to go out a few digits because I'm not at a final answer. Oh, I did a problem right there. Okay, this is positive 9. So I got a number times 10 to the negative 23, which should always be an indication the force shouldn't be that small. So let me fix that. So 2.158 times 10 to the negative 5th newtons. And this is specifically in the negative x direction, to the left. Okay, let's find F2. F2, the magnitude, and by the way, the coulombs in here cancel, the meters cancel, which leaves us with newtons. F2, we have our same constant. The two charges involved in this attraction are 4 and 3 nanocoulombs. Again, I'm using just magnitudes so that I can find, make sure I'm accounting for the direction properly. Like we did here, F1, negative I hat, well, that represents to the left. Okay, R2 has to be the straight line distance connecting these two charges. We have this top distance is 5, this side distance is 4. So R2 is going to be the square root of one side squared plus the other side squared. I didn't pick easy numbers this time that I would know the answer. I'm getting 6.403, and this is in centimeters because my 4 was in centimeters and my 5 was in centimeters. When I plug it into my force equation, I do need this to be in meters because it's going to cancel with the meter squared in the K units. So right now, this is just the magnitude of the force. I'm getting 2.631 times 10 to the negative 5th newtons. That's just how big that pull is. Okay. Direction. In order to find the overall force on Q3, we need to be able to add these force vectors together. And to do so, we need to have them in terms of x and y components, because we add x components to x components, then we add y components to y components. All right, so this F2 right here, let me draw that again. I'm just drawing it down here to have a cleaner picture. I can see that it points to the left and down. It has a negative x component and a negative y component. This angle in here, if I sketch our picture again really fast, it would be the same as the angle right here, just in terms of distances. The 5 centimeters, the 4 centimeters, the 6.403 centimeters we figured out. We can say that the tangent of this angle is the opposite side over the adjacent side using the dimensions of those distances. So inverse tangent of 4/5 gives us an angle of 38.66 degrees. So we now know this angle. If we want, we could substitute that in. F2 is this magnitude that we have solved for. So if I have the hypotenuse and an angle, I can certainly calculate for the sides. This x component is adjacent to the angle, so I will take the magnitude of the force, so the 2.631 times 10 to the negative 5th, and multiply that by the cosine of our angle. I will need to put the negative sign on it myself, which is fine. Because it points to the left. Using this triangle doesn't give me the negative sign. So here, this x component points to the left. It's 2.055 times 10 to the negative 5th newtons. The y component is opposite this angle, so this would be f sine theta to find that side. So same magnitude, sine of this angle that we figured out. It is downwards, so it will be negative. And you can wait to put the negative sign on until when you write it in vector notation if you want. That's actually what I usually do. So this component, 1.643, 1.644, gotta round it correctly. So we can say that F2 is negative 2.055 times 10 to the negative 5th I hat. The negative I hat means to the left, minus 1.644 times 10 to the negative 5th j hat. The negative j hat means down. So we now have the two forces individually that Q3 is experiencing because of the other two charges. So the overall force that Q3 experiences, we need to add these together. But we can't add magnitudes if they're not in the same direction. We can add x components to x components to get an overall x component. So both charges are pulling on Q3 to the left. So I'm getting negative 4.213 times 10 to the negative fifth I hat. So the overall pull to the left is what this represents. F2 is the only one that has a downward pull. And this is all in newtons. So this is the overall force in terms of the components. This is the force that Q3 overall will experience or feel because of the other two charges. Now, sometimes we might be asked to write the force in terms of the magnitude and direction. That's not how we have it written right now. Right now, we have it in terms of just the components, x and y. Magnitude and direction means if I were to draw these components, the x component is much larger to the left and the y component is down. So we have fx, we have fy. So our components, the overall force would be right here. This is the force overall. The magnitude is the hypotenuse. So how long the vector is. The direction is the angle this vector points at, which we can totally get. It's still right triangle that we're dealing with. We know the sides this time, though, instead of the hypotenuse and the angle. Now, I've already accounted for the direction the x and y components are pointing in with the way I've drawn the arrows. So I'm just writing the magnitudes, just the numerical portion. To find the overall force, the magnitude, we simply need the Pythagorean theorem. The x side squared plus the y side squared, square rooted, is going to give us this overall force. And this is specifically the magnitude. Plugging into my calculator, I'm getting 4.522 times 10 to the negative fifth newtons. So this is the magnitude. The direction or angle, I can say that the tangent of this theta that I've drawn in this triangle representing the overall force, tangent is the opposite side, so the y component over the adjacent side, the x component. So the 1.644 over the 4.213. Inverse tangent of both sides I'm getting an angle of 21.3 degrees. Now I can't leave my answer as just 21.3. So writing in terms of 2 sig figs, because I believe that's what we were given the numbers in terms of. The angle, this direction, goes back to polar coordinate system. In a polar coordinate system, we measure theta going counterclockwise from the x-axis. Since this is the 21.3, measuring all the way down to this angle, we actually need to add 180. So 201 degrees, so essentially 200 degrees in terms of 2 sig figs. If you've taken statics and you learned the notation where you draw the axis and then the arrow relative to that axis, that's fine. You're welcome to do that. And by the way, if you want to use the dimensions of the triangle for sine and cosine, so coming back up here where cosine would be, cosine of our angle would be the 5 over the 6.403, and then sine would be the opposite, so 4 over 6.403. That's totally fine as well. I find that most students at this point that come into the class are still not totally vector savvy, so I approach it the way we approached it originally in Physics 1. But the approaches you learn in statics and other classes with vectors apply as well. So this answer is in terms of a magnitude and a direction, an angle. If this was on a test, I totally wouldn't mind if you said 21 degrees below the negative x-axis, unless I specified the angle needed to be measured from a specific axis. Okay, I'll do some more examples in separate videos. I apologize, this video has ended up very long, but practicing is typically the most important part. The equation itself is not terribly difficult to use, but we do have to understand what each piece means. And then as soon as we have more than more than 2 charges, it gets more involved, of course, because we have to use this equation over and over and over again for every force that the charge we're asked about is experiencing. So see the additional examples if you want some more help with vectors